is Cauchy's root test. When we have whole power in un term, we apply Cauchy root test. When ratio test fail, we have four choices. But if Cauchy's root test fail, we have no choice. We have to use necessary condition for convergence. See how, what is the definition, what is statement of Cauchy's root test. If series un is a positive term series and limit n tends to infinity, nth root of un is L, then un is convergent if L less than 1. Here it is opposite of ratio test. In ratio test, convergent if L is greater than 1 and divergent if L is greater than 1. Note, if L equals to 1, test fails. Then apply necessary condition for convergence of a positive term series. Ratio test fails, then we have four choices. But if root test fails, we have no choice. Only we can apply result if limit n tends to infinity, un is 0 implies convergent, not equal to 0 implies divergent. Don't apply it directly. See one example. Examine for the convergence or divergence of the series its solution. The given series is see, it is whole power n. If we have, whenever whole power is n here, n cube, we use root test. This is whole power. Take nth root on both sides. N power cancel out with nth root. We are left with separate the terms. N will cancel out. Take limit 1 by 2. 1 over infinity, 0. 0 into something. 0. What we get? 1 by 2. Log infinity is not defined. So 1 over infinity is 0. 0 into something is 0. 1 by 2 is less than 1. Therefore, by Cauchy's root test, series UN is convergent. Now see second part of the question. Very easy. Here UN is separating the bases. Separating the bases. This power is negative. When we take it in denominator, it will become positive. Or you can say it is whole power n. Whole power n. Take nth root. Power will cancel out with nth power. Its power 1 by n. Now see how we can simplify it. See. See, minus 1 raised to power infinity. N is infinity. It is either minus 1 or 1. If n is even, it is 1. If n is odd, it is minus 1. Okay. And this is minus 1 or 1 means something, and over n means something over infinity. It is 0. So it is 5 raised to power 0. Anything raised to power 0 is 1. 5 into 1, 5. 1 by 5 is less than 1. Therefore, series is convergent by Cauchy's root test. See one more example. Examine the convergence of the series plus so on. The given series is suppose it is summation un. Now see, first term of the given series is not matching with other terms of series on account of symmetry. As power of first term is 1, again power of second term is 1, then third term is 2, and so on. So we neglect it. If we add or subtract in infinity, it does not get affected. So neglecting the first term summation un is neglected. We get so un will be see for u1 we have 2, for u2 we have 3, for un we have n plus 1. In denominator we have plus 1 of numerator, plus 1 of numerator, plus 1 of numerator will is n plus 2. See power. For u2 power 2, for u3 power 3, for n power is n. For first term power of x is 1, for second term power is 2, for nth term power is n. Let it be first. On account of symmetry, you can check whether u1 is correct or not. Put n equals to 1, we get u1. Put n equals to 2, we get u2. Therefore, it is correct. Now, whole power is n. So, we can apply Cauchy root test. Take nth root. Now, take higher power of n common. N will get cancelled out. Now, take limit. 1 over infinity 0, 2 over infinity 0, 1 plus 0, 1, 1 plus 0, 1, 1 over 1 is 1. So we are left only with x. Therefore, by Cauchy's root test, series un is convergent if x less than 1 and divergent if x greater than 1. When x equals to 1, test fails. Test fails. From 1, un. Put x equals to 1. X equals to 1. Take higher power of n common. This will get cancelled out. Take limit. We know the result. It is e raised to power ab. So when we apply limit, it will become e. When we apply over here, it will become e square. 1e will get cancelled out, which is not equal to 0. Therefore, by necessary condition for convergence, series UN is divergent. Therefore, series is convergent for x less than 1 and divergent for x greater than equals to 1.